Alright, so let's start with vectors and vector spaces. Vector spaces are a special kind of sets. Sets together with some additional algebraic properties. Now, sets are a fundamental object in algebra, and sets together with some structure make it either a vector spaces or maybe groups, rings, fields, or maybe a combination of these. So what is a vector space? A vector space V is a collection of objects with an addition and a scalar multiplication, and these are defined so that these operations are closed inside the set, which means that adding two vectors gives me another vector in the vector space itself, and multiplying a vector with a scalar gives me another vector in the same vector space. Now, what is a scalar? A scalar is a field element, an element from some field. This field can be the field of real numbers, complex numbers, or any other field like finite fields, and so on. So, these closure properties can be stated as follows. When alpha and beta are scalars, then alpha plus beta of x is alpha x plus beta x for all vectors x in this vector space V. There is an associativity linked to scalar multiplication, which is this. Also, vector addition. This plus is vector addition is commutative. So x plus y is y plus x for vectors x and y. There is also associativity related with vector addition. So it does not matter where we put the brackets. And there is distribution property with respect to scalar multiplication. So alpha of bracket x plus y is alpha of x plus alpha of y. Moreover, there exists something called a zero vector in the vector space V, such that addition with the zero vector gives me the vector itself, and multiplication with the zero vector gives me 0. And because a vector space is defined over some field, there exists an identity in the field, and that identity, when multiplied with the vector, gives me the vector itself. Thus, we can say that if x and y are vectors in V and alpha and beta are scalars in F, then alpha x plus beta y belongs to V. This is the closure property. Now note that this plus alpha plus beta, this plus is in the field. This is the field addition. Whereas x plus y over here, this addition is the addition in the vector space. This is addition of vectors, this is addition of scalars. So what are some of the examples of vector spaces? One of the most common examples is Euclidean spaces. That is the familiar plane and planes in higher dimension, such as R2, which is an ordered pair of two real numbers, Rn, an ordered tuple of n real numbers. Similarly, for C2 and Cn, tuples of complex numbers. Another interesting vector space is the space of all polynomials of degree n, which is written in this way: summation over j, aj, xj up to n, where the a, j's are real numbers and x's are some variable. Note that this space Pn also includes polynomials which are of degree less than n. We can check whether this is a vector space or not. If we add two polynomials of degree n, it still is a polynomial of degree n. And if we multiply a polynomial of degree n with some scalar, some real number, that still gives me another polynomial of degree n. And the other properties, such as existence of a zero polynomial, which is just zero of the field, that is the zero vector, associativity, commutativity, these can easily be checked. Another example which is important in analysis is the LP space, the space of infinite tuples of numbers, such that the absolute value raised to the power p and their sum is less than infinity. These can specifically be called LPR or LPC depending upon the entries in the tuples. And there also exists something called trigonometric polynomials, which is of this form. Now in the Euclidean space Rn, there exist some standard vectors E1 to En, where this number 1 or 2 or 3 signifies a scalar 1 in that position. E1 means 1, 0 all the way to 0 n places. E2 means 1 in the second place, and so on. These, as we will define later, are standard basis vectors. We will see what bases are for a vector space in a little while. Geometrically, this can be seen as usual. E1 and E2, these can be seen as coordinate vectors along x and y axis. And we can draw vectors in the Euclidean space with the help of these E1 and E2. And also we can add vectors in such way, as we have seen earlier in physics and high school coordinate geometry. Now, in algebra, a very important notion for some object is that of a sub-object. A sub-object is a subset which inherits the properties of the superset, inherits the algebraic properties of the superset. Thus, in vector spaces, such a subset, which is a vector space in itself, is called a subspace. We can also use linear subspace to denote that this is a vector space. So, formally, if V is a vector space and U is a subset of the underlying set of V, then we call U a subspace of V if U is closed under vector addition, closed under scalar multiplication, and satisfies all of the vector space axioms. Some of the examples are, if we take V to be R3 and U to be all triplets of the form AB0, this ordered triplet, such that AB belongs to R, then we can see that U is a vector, is a linear subspace of vector space V. We can add two vectors in U and it will again form a vector of this form, because 0 plus 0 will always give me 0, and multiplication will also give me a vector of this form, and other axioms can easily be checked. Now there exists a notion of something called span. But before span, I should say what linear combination are. A linear combination is an expression of this sort, where I take some vectors and I multiply those vectors with all possible scalars, and then I add those vectors. So this will give me a set of vectors, and that set is known as span of a subset of the vector space. So if S is a subset of vector space of this form v1, v2 till vk, where each vi is in the vector space V, then a linear combination of all these vectors, which is called the span of S, is an expression of this form, summation over j, aj, vj, up to k. So all such linear combinations will give me span of this subset. As I said, we can say U is a linear combination of V1 to Vk if U can be written in this fashion, A1 V1 until Ak Vk, where these AIs are scalars. Now you see a theorem that if V is a vector space and U is a subset of V, and if U is closed under vector addition and scalar multiplication, then U is a subspace of V. This is somewhat tautological, as this follows from the definition of subspace. This corollary also simply follows that if V is a vector space and S is written in this way, it is a subset of V such that it contains k vectors, then the span of V of this S is a linear subspace of V. Now we know that span of V is written as all possible linear combinations of this sort. Now this means that if I take two such linear combinations and add them, then it will add coordinate wise this way: a1 plus b1 of v1 plus dot 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 ak plus bk of vk. Now this again belongs to this span, so it is closed under addition. And similarly we see that it is closed under multiplication. C of V is C times all these. C A1 V1 plus dot 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 C AK VK. And this again is a linear combination of V1 to Vk. And thus we see that this CV again belongs to span of S. Hence, we can say that this span is a linear subspace of V. Another notion is that of product spaces. So, if we take Cartesian product of the underlying sets of the vector spaces and we define vector addition as addition component wise, that is v1 w1 plus v2 w2 is v1 plus v2 w1 plus w2, and scalar multiplication also component wise, a of vw is a of v and a of w. Then with these two operations, the Cartesian product Z, which is v cross w, becomes a vector space, as we can easily check. So this is also called a product space, product of two vector spaces v and w. This is an easy example. Now, an important notion which is called linear dependence or independence. Now consider a linear combination of this sort. We say that a set S, which is a subset of a vector space V, is linearly dependent if there exists some scalars a1 to ak, not all of them 0. Some of these scalars are non-zero, such that this linear combination a1 plus v1 until ak plus vk is equal to 0. So, this means that some linear combination of v1 to vk gives me the 0 vector. And if that happens, then I say that S is linearly dependent. For example, suppose I consider the vector space of real numbers, just R. Then any two real numbers are linearly dependent. A set consisting of two real numbers is linearly dependent. That is because if I take any real number x and another real number y, then I can always get scalars a and b such that ax plus by is 0. Now there comes a proposition. If S is a subset of this form of a vector space V and it is known to be linearly dependent, then at least one member of this set S can be expressed as a linear combination of the others. This follows from the definition of linear dependence. Because these vectors are linearly dependent, I can write these as a linear combination such that it forms the 0 vector. Now, since not all of these coefficients are 0, we can always take one of these monomials to the other side such that its coefficient is non-zero and divide by its coefficient to get that monomial in terms of the others. So suppose, without loss of generality, that a1 is non-zero. So we can take a1 v1 to this other side, and that will give me minus a1 v1, and I divide throughout by a1. Then that will give me, or minus a1. Then that will give me minus of a2 by a1 v2 plus dot 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 minus of ak a1 vk, and that will be equal to v1. So v1 has been written as a linear combination of v2 to vk. So actually we have shown that there is no vector with a unique representation in GS. So with the help of this proposition, we can see that v1 can be written as a linear combination of v2 till vk, and it could have been done by other ways too because of linear dependence. Now another corollary is that if 0 belongs to this set S, if one of these vectors is the 0 vector, then S is automatically linearly dependent, because I can take, suppose vk is 0, I can take all the other coefficients ai's up to k minus 1 as 0, and any non-zero coefficient of vk, and if I add them, I'll get the 0 vector, because a1 v1 plus ak minus 1 vk minus 1 is 0 because all the coefficients are 0, plus ak vk is again 0 because vk here is 0. So I am always getting a 0 vector out of the linear combination of the vectors in S. Thus if 0 belongs to some set, then that set is automatically linearly dependent. Now what do we mean by linear independence? A set S of this form is linearly independent if the only way to write a linear combination of these vectors as a 0 vector by taking all the coefficients to be 0. So 0 has a unique representation in terms of the vectors in S, and that is the trivial representation where all the scalars are 0. That means the only way 0 equal to a linear combination of v1 to vk is 0 times v1 plus 0 times v2 plus dot 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 0 times vk. This is a very important idea. So we see that linear independence means inability to write 0 vector as a non-trivial combination, linear combination of other vectors. The only way is the trivial combination of all zeros. Now comes the important aspect of basis. But first, a definition. Let V be a vector space and S a subset of V. We call this S a spanning set if the span of S a spanning set for this subspace U if the span of S gives me the whole subspace U, and if the spanning set of S gives me the whole space V such that S is also linearly independent, then S is a basis of V. So a basis is a subset of a vector space which spans V and which also is linearly independent. This means that if S is a basis, then every vector has a unique representation. Why so? Because if I take any vector V, small v, in the vector space capital V, then since S spans capital V, I can write small v as a linear combination of the vectors in S in this way. Now suppose there exists a second type of linear combination other than this A1 V1 plus AK VK. So contrarily, we suppose that there are two ways to represent some vector V. That is, we suppose that this representation is not unique, approved by contradiction. Suppose this is another way to write it, B1 V1 plus BK VK. Now if we subtract these two expressions, we get 0 in the left hand side and A1 minus V1 B1 times V1 plus dot 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 AK minus BK times VK. Now we know that S is a basis, so S is linearly independent. Thus only way to write 0 as a linear combination of V1 to VK is the trivial linear combination where all the scalars are 0. Thus A1 minus B1 is 0, A2 minus B2 is 0, and so on, AK minus BK is 0. Thus we see that A1 is equal to B1 and so on, AK is equal to BK. Thus these two representations are the same. Examples. As I said earlier, if I take V as R3 and S as E1, E2, E3, that means E1 is 1, 0, 0, E2 is 0, 1, 0, E3 is 0, 0, 1 column vectors, then S is a basis of V. How do we check that? We can check that using this proposition. I take 0 vector and try to write it as a linear combination of E1, E2 and E3. Then this is of this form, 0, 0, 0. 0 vector in V is actually a column vector in R3, 0, 0, 0. And this can be written as A1. E1 is, as I said, these column vectors. And after addition, it comes out to be A1, A2 and A3. Now the only way possible for this equation to hold is that each A1, A2 and A3 is 0. And thus we get linear independence because this turns out to be the trivial linear combination. So we saw what a vector space is. It is a set together with an additional structure of closure under addition and multiplication, such that some other properties are satisfied, like associativity, commutativity, existence of a 0 vector, and so on. we saw what linear combinations are. Just a way of writing a vector in terms of an addition of some other vectors. So a linear combination is just a, a combination of vectors together with addition in between them. And we also saw what span is. A span is all possible linear combinations, all possible way to write it as polynomials of degree 1 of vectors, so to say. And then we saw what basis is. A basis is a special kind of a spanning set. That is a spanning set which is also linearly independent. Next, we will see what linear transformations are. Again, in algebra, we have the notion of mapping or functions given to sets, given to algebraic entities. We want to move it in between these sets. If these sets are vector spaces, then the mapping is called linear transformation. If these were groups, then it would have been group homomorphisms. If rings, then ring homomorphism. If these were categories, then it would have been functors, and so on. So now we concentrate on linear transformations. Before that, let us recall what functions are. In high school, we have studied what functions are. So functions is a special kind of rule that associates an element from some set X to a unique element to the target set Y. So if X and Y are sets and small x belongs to capital X, then the image of small x under f, that is f of x, belongs to capital Y, and that image is unique. It can't be that x maps to small y1 and small y2 simultaneously. Think of it as mapping. If I have a map of some city, then every point on that map points to some specific location in the city. It can't be that some point in the map is pointing to two different locations in the city. That would have been misleading. It would not be a very good map. So, analogously, a mapping or a function in mathematics is defined to have a unique image for every pre-image. Elements. So, x is called domain of f, the function. Y is called the codomain. Elements in the domain are called pre-image. And the elements in the codomain under f are called image. And the set of all these images is called the range. These things we have seen earlier, maybe not rigorously, but we have worked with them in high school. Now, as functions are defined between sets and vector spaces are actually sets, so we can legitimately define the notion of functions on vector spaces. But since vector spaces are sets of some special kind, functions on vector spaces will also be of some special kind. That is, they will satisfy some special properties. And what are those properties? A function on vector spaces is called a linear transformation if these properties are followed. That is, if I take two vectors in the domain vector space V, then adding it first and then transforming it will give me the same effect of transforming those vectors first and then adding them. That is, T of u plus v is equal to Tu plus Tv. Note that u plus v is a vector in capital V. This u and v are vectors in small v. U and v are vectors in capital V, and their addition will also give me a vector in capital V. This is because V is a vector space. And transforming that vector u plus v will give me a vector in this codomain space W. And moreover, Tu and Tv are also in W because u and v are in V. Thus, we see homogeneity in terms of this addition. That is, first I add and then transform. First I add over here and then transform is the same as transforming the two vectors first and then adding. This is the first condition. Second condition is similar to the first condition in the sense that we can first multiply a vector in the domain vector space and then transform. That will give me the same vector in W as first transforming and then multiplying with the scalar. So T of Cu which is in V will give me C of Tu and Tu which is again in V. This is kind of redundant because we can just take U plus U and so on, U plus U plus U C times, and we will get this property, but only for natural number and integers C. If C were real numbers or real numbers, I mean pathological real numbers such as irrational numbers, then we cannot add a vector irrational times. So redundant for integers, integer C, but not for others. So we have these two properties. Might seem redundant, but in its greatest generality is not redundant. Examples of linear transformations. If V and W are two vector spaces, we can define a function t from V to W as T of V is 0 for every small v in capital V. This is a constant function and it points to 0 vectors for every element in the domain. This we can check to be a linear transformation. Why? Because if V1 and V2 are two vectors in V, then T of V1 will be 0, T of V2 will be 0. Adding them will give me 0. And V1 plus V2, another vector, whose image under T will again be 0. Similarly for scalar multiplication. Another trivial example is that of identity transformation, where everything maps to itself. That is, if I take a transformation T from the vector space V to itself, then I define T as T of V is V, then I can check that this is a linear transformation, and it is called a identity transformation because the image is identical to the pre-image. And another nomenclature of linear transformation from a vector space to itself is also called a linear operator. So T can also be called a linear operator. Now some properties of linear transformations. So let V and W be two vector spaces. T as usual is a linear transformation between them. Then T of 0 is 0. So this 0 on the left hand side is the 0 vector in V, and this is the 0 vector in W. So 0 vector in the domain space points to 0 vector in the codomain space. How? T of 0 is equal to T of scalar 0 times vector 0 by the second property of linear transformation. And by the second property, this scalar 0 can be pulled out. And by the property of vector spaces, scalar 0 times any vector gives me the 0 vector. So we see this. Another property is that T of minus V is minus of T of V for all small v in capital V. Again, we can use pulling out of scalars to prove this. Another property is that Tu minus Tv is Tu, U minus V is Tu minus Tv. This too can be followed from the property of linear transformations and this property from the definition of linear transformation and this property. And another important property is that if V can be written as a linear combination of V1 to Vn, then T of V will be written as a linear combination with the same scalars, same scalar coefficients. This is actually proved by induction. We see that for n equal to 1, this turns out to be true from the definition of linear transformation. And I suppose that this turns out to be true for some n minus 1 of the vectors. And then I take n of these vectors and I consider its image under T. That image can be broken down in this way because this is one vector, whole of this is one vector and this is another vector. Since it was proven up to n minus 1, it holds for n equal to 2. And then since it was true for n minus 1, we can pull out these C's, C1, C2 out of this transformation, and this gives me a combination of this sort C1 TV1 till Cn minus 1 Tvn minus 1, and this is a single vector, and by the base case we know this is true, so we can pull out Cn, and we by associativity of vector addition we can get rid of this outer bracket, and then we will get C1 T of V1 until Cn T of Vn. Now there exists a very deep relationship between matrices and linear transformations. We will see that left multiplication by a matrix to some column vector is a linear transformation. So left multiplication by a matrix is a linear transformation. Moreover, we will also see that every linear transformation between finite dimensional vector spaces is achieved by some matrix operation. So here, suppose A is a matrix of size m cross n, and then given a vector v in the Euclidean space Rn, we define T of v to be A times v. Then we can see that T is a linear transformation from Rn to Rm. This can be easily checked by the notions of matrix addition, matrix multiplication. We know that multiplying a matrix with two vectors u plus v with a vector u plus v, this matrix multiplication can be distributed over this addition. And this means T of u plus v is Tu plus Tv. And similarly, we can pull out the scalar, and this will give me C times this matrix A times u. Thus, T of Cu is Ctu. So, T is a linear transformation. Another important geometric notion is that of projection in Euclidean spaces. So suppose V is some vector, usually non-zero vector in the Euclidean space Rn. Then for some other vector u in Rn, we can define the projection of u on V as the dot product of v and u, this is a scalar, divided by another scalar mod of v square times the vector v. So this is a vector along the direction of v but scaled to some length. And this length is actually the projection of u on v, the shadow, so to say, of u along v. We can see that projection is actually a linear transformation, because projection of u plus w is actually projection of u plus projection of w. We can replace u here by u plus w and dot product distributes. So this comes out. Similarly, we can take cu over here and c will come out of the dot product, and we get c times projection. So projection is a linear transformation. This idea of projection is important because using projection we can write any vector u as a sum of a vector along v and another vector which is perpendicular to v. In this way, u can be written as projection of u along v and projection of u along a perpendicular direction of v. We can check that this expression u minus projection vu is actually perpendicular to projection u along v. If we take the dot product, then it has to come out to 0. as you can replace this sign with a dot product, and you will see that u dot projection u along v, this one of these will come out to be 1 and one will come out to be minus 1, and we will get 0. Another example is transformations of this sort, where v1, v2 and v3 are transformed to 2v1 plus v2, 2v2 minus 3v1 and so on. We compute t of some vector using this formula. Another exercise is that whether the transformation given in this way is a linear transformation or not. T of xy is x square y, where t maps from R2 to R2. We take two vectors x, y and zw and we transform them. Then x, y plus zw is actually x plus z plus and y plus w. Now this under transformation will give me x plus z square y plus w, but this is not equal to x square y and z square w, because this will have a 2x z term, so this is not equal to t times xy plus t times zw. Geometrically speaking, a linear transformation takes lines to lines. It might scale them or rotate them, but lines won't become circles or nonlinear curves. Lines will always go to lines. And a trick to quickly detect whether some transformation is linear or not is to check whether the exponents are necessarily 1. If there is an exponent which is more than 1, then the transformation can't be linear, because line won't remain to line, as we have seen in conics, that the equation of lines are linear expressions, while quadratic expressions can denote parabolas or circles or hyperbolas and so on. Thus, we could have easily said that this is not a linear transformation, but still we need to rigorously show that this is not a linear transformation. Alternatively, you can also check that the scalar multiplication is not preserved, because c would have come out as square of c, and numerically also this would not have preserved. So one counter example will suffice to show that this is not linear. We can have any counter example of this sort. This is another easy exercise where it is given that something is a linear transformation, and we are given the images of basis vectors, standard basis vectors, and we are to compute the image of some arbitrary vector. Now we will write the arbitrary vectors in terms of a linear combination of standard basis vectors, and then we will find out where these standard basis vectors go and add them to get the result. So we see, with the help of this example, we can see that a linear transformation between two vector spaces can just be defined by assigning the images of basis vectors. In calculus, to define a function on sets, we either had to give an explicit formula for defining the function, or we needed to know where each element was going, where each element was mapping to some image. Like in groups, a bijection between two sets, a combination of these forms a group, and each to specify each bijection we need to know where each element is going. So that is quite cumbersome in vector spaces, because there are infinitely many elements in a vector space. So usually there are infinitely many elements in a vector space, and it becomes impossible to specify where each element is going. Thus, a feasible way to specify or characterize a linear transformation is to just tell me where each of the basis vectors are going. And if I know where each of the basis vectors are going, I will know where any other arbitrary vector is going, because I can write any arbitrary vector in terms of those basis vectors, and by linear combinations and pulling out the scalars, I will see that where the image of any arbitrary vector is going under the linear transformation. Now these are easy exercises. We take some matrix of this form, specify some linear transformation as left multiplication by the matrix, and we want to compute where some vector in R5 is going. So this is just a high school computation. Similarly, we can compute the pre-image using Gauss-Jordan form, as we might have seen in a first course in linear algebra that uses just matrices. This is actually a second course in linear algebra, where these are the theoretical underpinnings of linear algebra, which uses vector spaces. There can also be a third course which uses modules and so on. Now we come to an important notion called kernel and range of a linear transformation. To every linear transformation T from V to W, there exists two special subspaces. They are the kernel and range. The kernel of T, which is also denoted by ker T, is the set of all those vectors small v in the domain space V, such that the image of this small v under T is 0. So in set builder form, I can write it as ker T is equal to all those v in V such that Tv is 0. You can easily check that ker T is a subspace of V. And range of T is actually a subspace of the codomain space. So in the set builder form, range of T is all those vectors in W such that this should have been W. All those W in W, small w in capital W, such that small w can be written as an image of some V, some small v in capital V. So W's are actually images, as we see in functions in high school notion of function. Range of T is actually the set of images under T, and this range of T forms a subspace. This too can easily be checked. If I take W1 and W2, two image elements, then those image elements will be images of some V1, V2. W1 plus W2 is actually TV1 plus TV2, and by the definition of linear transformation, that will be equal to T V1 plus V2. Similarly for scalar multiplication, so it can easily be checked that range is actually a subspace of W. So we get a subspace of V and a subspace of W. The special subspace of V is kernel T, and the special subspace of W is range T. Now, another important notion in algebra is that of isomorphism. Maybe there are two algebraic entities which are not equal, but they behave equally. They have all the equal properties. They have all the equal algebraic structures. How do we know and ascertain that they are equal? How do we know whether they belong to the same class? That is known from the notion of isomorphism. So an isomorphism is a special kind of function which is actually both one-to-one, that is injective, and onto, that is surjective. So this makes T into a bijective function. So if T is in vector spaces, T is a linear isomorphism if T is a bijective linear transformation. And we can prove that T is an isomorphism if and only if kernel of T is 0 and range of T is W. So kernel of T 0 implies that T is an injection, and range of T equal to W implies that T is a surjection. This follows from high school function theory, and this requires a proof. Now, as I said, that every linear transformation between finite dimensional vector spaces is actually obtained from operations of matrices. Now, this matrix can be obtained by seeing the images of the basis vectors under this linear transformation. So this we will see next time, that how matrices come in play when considering linear transformation of Euclidean spaces, and how an analogous and very similar notion is carried over to any arbitrary finite dimensional vector spaces. In particular, the coefficients of vectors in V are taken as column vectors, and images of those column vectors in W form another column vector, and those columns are arranged in the form of columns of matrix, and that matrix is actually the matrix of linear transformation. So we just need to know what the matrix of linear transformation is, and we will know the behavior of the linear transformation. That is, we can take any vector v, express it as a linear combination of basis vectors, so we will get some scalars, a column vector of scalars, and if we know the matrix A of linear transformation, then we can left multiply A with that column vector to get actually the column vector in W, which is the column of coefficients of the linear combination of vectors in the basis in W. So we will know where some small v is going under T. So this powerful notion helps us compute very effectively what the behavior of T is. So today we saw what vector spaces are, span, linear independence, basis, and functions of a very special kind called linear transformation between vector spaces, and that every linear transformation comes with the data of a matrix. Thank you.